Cool. Hey everyone, how are you doing? I just had to debate standards in machine learning this morning, so hopefully I won't forget what I'm talking about and start delivering the wrong talk. Yeah, the talk will be precisely on this. There's some, I've spent a lot of time recently working on active learning, and active learning and efficient exploration have something in common, which is that they're both tend to be guided. I guess you could even both characterize them, at least colloquially, as some kind of exploration. One of maybe like input space, and one of your environment. And in both cases, the strategies that we try to come up with tend to be governed by some way of quantification of the model's uncertainty, some notion of we want to visit regions where we're not certain about the reward, or we want to try policies where we're not certain about how good it is, or we want to collect preferentially examples where we feel like we haven't seen examples like that, or we're not confident in our prediction of the label. So there's a bit of overlap, if only methodologically. Active learning being even simpler might give us a simpler test bed to start evaluating some of these uncertainty estimations and see how good are they actually. I got interested here in that we sort of, on one hand, we were really good at video games and doing supervised learning with huge amounts of data, and it seems like a lot of problems are solved, and then you go work at a company and you look at the kind of lofty things that you say we want to do. We want to build chatbots that are going to use this reinforcement learning, and suddenly it becomes problematic that we don't have 100 million training examples, or we can't, at some point we would sort of sully the reputation of our chat product long before we actually had a chance to find a good policy. So, in real world interacting systems, giant amounts of data, especially if they require interaction with humans, can be prohibitively difficult to collect. That was the kind of problem I started working on. This is work that I actually did while I was still a PhD student during an internship at Microsoft Research. I did a couple papers I'm going to talk about. One on efficient exploration, using uncertainty estimates from Bayes by backprop networks, yielding the horrific acronym BBQ nets. And another on trying to avoid the problem of successively repeating catastrophic mistakes, basically, as you continue to explore, owing to the combination of exploration and function approximation. And this latter one was work that, sort of been ongoing work that we've been developing as our ideas crystallize a bit. So it started when I was at MSR, and it's continued with different cast of collaborators, including Kamyar, who's, no matter how well I know, no matter how close to a brother he is, I'll never pronounce his last name correctly, but I'm going to say something like Aziza Denisheli. Pretty good, yeah. Better than in the past. I've been exploring the space of pronunciations and slowly collecting reward signal. So I'll talk a little bit also then about using cases where we've used some of the same tools for uncertainty estimates, but we've looked at things. One, to what extent can we get big gains doing active learning and named entity recognition? And a subsequent paper that I just did with a master's student at CMU, Aditya Siddhant, about basically the sort of settings that we have set up even for active learning, which is quite a bit maybe simpler than reinforcement learning, are still a bit contrived, right? We sort of set up this thing where we know the labels are actually used to compute the model that we have, then we cover our eyes and pretend we don't see the labels, and then explore the unlabeled examples. And there's a huge amount of information leak to try to see like just how close are we to policies, the acquisition functions that we could actually use. So the first paper I'll describe is work with my MSR collaborators. And basically we were looking at this issue of what we call like task-oriented dialogue systems. The team that I was on was a language team. They were excited about things that were happening in reinforcement learning more broadly, but generally in the, evaluated in terms of board games and video games. And they were interested in dialogue systems. And there's sort of a large spectrum of what people mean by a dialogue system. On sort of the right hand, that's I guess a low point in our field, but I guess it wasn't actually in our field, which just gave us a bad name. We have chit-chat bots, like this sort of aspiration that's sort of only fuzzily defined of creating general purpose interlocutors, right? Like I want something that'll pass the Turing test or something. The problem is nobody really knows what we're optimizing there with completely open-ended free-form dialogue. And then on the left, you have this much more modest goal that we're actually doing pretty well on, which is basically like single-turn dialogue bots. And we sort of able to solve this with slot filling systems. So basically, you say to Alexa, please play this song by this artist, and then it does it, and then the dialogue is over. And if you ask it, who is the artist I just played the song by, it doesn't know. And if it doesn't ask you, in general, many clarifying questions, and if it does, it was because they were hand-programmed, because actually, as much as we in this community talk about the death of rule-based systems, are actually alive and well and are what actually powers most dialogue systems in practice. So a typical dialogue system pipeline looks something like this. So the user is conversing with a system. I really should have put like the information coming out from the bottom where the mouthpiece is, not from the earpiece, but you can use your imaginations to turn the phone upside down. So the user is going to say something. We're going to get free audio. You can imagine you can add one layer where you'd also have speech recognition and speech synthesis, but we'll just ignore that for now. Let's say we get even text, but it's free-form text from the user. We have what's called a language understanding unit. That's kind of a loaded term, but really what we just mean is like slot filling. So we're going to turn free-form text into kind of structured utterances according to some kind of pre-specified like templating format. In our case, we were interested in helping someone to book a movie. So like it might be your core acts could be like request, inform, answer, or something like this, thank, greet. And then each act could be associated with some number of slot value pairs. So predicting what are the slots and the corresponding values in the text, usually through some kind of like sequence tagging system. We have a language understanding unit. It's going to pass data to a state tracker, which is going to accumulate some kind of representation of the overall state of the dialogue, including like maybe the state of the database and how certain slots might match against some movies that are playing or not playing. And at the end, we have this dialogue policy, which is responsible for choosing what is basically the high-level action that you're going to take next, right? Are you going to ask them a question? Are you going to inform them about something? Are you going to give them a list of movies that are available? Are you going to ask them what city they're in? You end up, in our case, we have an action space of like 50 to 60 like high-level actions. And in typical dialogue systems right now, what you end up having is like, this is like the great hope, and I think a lot of the dialogue community is that you're going to use reinforcement learning over here on the policy side. But the way things usually work right now is almost all the machine learning is taking place on the speech recognition side. On the language understanding side, it's a little bit easier to get away with just using some kind of templating for the generation side, although some people want to use machine learning to like make more natural language generation. But the dialogue policy tends to be a rule-based system, and that's what like our hope is to say, could we train a system more efficiently that like without getting a million people angry at us and like writing angry tweets, actually get to the point of having a policy that'll perform better than a rule-based system. Things are going to look like this. We're in this space of each episode is we can think of like our observations like corresponding to the representation of the state of the dialogue after each utterance that comes from the user. So we're looking in the range of an episode length of like 10 to 20 steps. The tool that we like to use is reinforcement learning, which you guys are all eminently familiar with. We have an agent. We're going to consider some action space in this case. The actions are like the 60 high-level actions that we have. Our environment is actually just the state of the dialogue. And our rewards are going to be basically at the end of the dialogue, one of the actions is you can like select the movie that system thinks is the best match based on the available information and basically book the movie. So this is the user wants a movie and we book the movie. And our user simulator, or in our human trials that we did, like the actual people who had something in mind, if you booked the correct movie, you get some very big reward. If you did not, you get a reward of 0. And then additionally, we say that we want to encourage pithy dialogues, right? Like if someone could book the movie, if you give all the information in the first utterance, you say, I want to see precisely this movie at this time in this theater, and the system books it on 1 turn, that's a lot more useful than if it books it in 20 turns, right? So we want to encourage short dialogues. So it's a very simple reward function. We're going to use DQNs, right? Which we sort of knew were awesome at games, but we wanted to know can we get something that's going to work without taking squillions of exploration steps. So, right, we can think of sort of everything as living inside the environment except for this vector representing the state that we get back after each turn. So the user simulator, the knowledge base, the state tracker and all, and the agent, which is choosing its actions. Right, I guess you're at the exploration workshop. I don't need the slide. It tells you that efficient exploration is important, but I think it's worth considering in these real cases, like just how impossible it would be to take a system that has to just kind of collect like 10 million interactions. Now, one problem here actually is that the primary reward signal is sparse. So a randomly exploring policy might never actually encounter the reward signal. So we have a simple heuristic that at least is able to sort of spike the replay buffer and get the system to have its first success sooner. That makes a dramatic difference. But basically all of our policies kind of tap out without having ever successfully done their job if we just kind of start off from completely random exploration, start off from a completely empty replay buffer. Right, so our idea that we started with is to say, rather than doing epsilon greedy exploration, let's do Thompson sampling. And our idea is to say, we want to choose each action according to the probability that is the best action. The conundrum is that our models which are best at parameterizing the value function are not the models for which we have like the most developed science of extracting uncertainty estimates. So this brings us into the familiar case that you see with lots of us in this field trying to come up with different ways, different techniques that we can use to extract uncertainty estimates, which we could then use to guide exploration. The tool that we used in this case were the Bayes by backprop networks developed by Blundell and colleagues at DeepMind. And the idea is really quite simple. It just says that rather than just having a point estimate for each of the weights, we're going to assume some very, very simple variational distribution that's going to now have our estimate of each weight actually represented as a distribution, where we're just going to be super simplifying, make each one an independent Gaussian. And we're going to say we want to choose the distribution for each weight such that they minimize some divergence from the true posterior. Of course, I think there's all kinds of reasonable objections that people bring up of once we make such grand simplifications, what are we really doing? Maybe it's just max likelihood with a fancy regularizer. But ultimately, this is an empirical paper, so what we can ask is, does it work in practice? At training time, now we have this stochastic neural network, right? Its outputs are actually the way we're going to generate outputs. We have a distribution over each of the weights. So to make a forward pass, we're first going to sample a set of weights from the distribution over the weights. Then we're going to feed our input through, and then we're going to get an output. And if we generated multiple samples of the weights and fed the input through multiple times, then we could get a distribution of outputs. In this case, what we just want to do is sample an action according to the probability that it's the best action, at least given the current policy otherwise. So we only need to do one sample at exploration time. At train time, what we're going to do is we need one network to generate the target, one network, the one that we're actually updating. One thing that we found worked better was just to use the map estimate, which in this case is actually just use the mean of each of the Gaussians to generate the target. But to then just make, and also to make one sample from the network that we're updating. It turns out if you make many samples, this becomes a computationally expensive bottleneck in the process. So Bayes by backprop, at least when we're just trying to estimate uncertainty over our parameters, like fixing the data set, tends to give us things that look, at least when we create toy examples, kind of like the sort of uncertainty estimates we'd like to see. The variance of the outputs then does tend to blow up sort of outside the region of observed data points. This is like a simple like 1D example with a 1D input, 1D output from the Blundell paper. To get a feeling for why it's not enough to just do stuff like bootstrapping, one thing that could happen is that if you actually train across many different runs of a regular neural network, they all kind of tend to tell you, they don't have like high variance in the regions where you don't have data. They kind of tend to have similar outputs. So you wind up being sort of, thinking you're reasonably confident if you estimate the variance in that way. In fact, in this case, it's this weird behavior where the further away you get from the data, the more confident the neural network thinks it is, if you take confidence to be the variance in the predictions. So in terms of applying this to reinforcement learning, I don't want to over glamorize what we're doing here. There's some dirty hacks. Like for one, what we really want ultimately in principle, right, is to have some uncertainty over the value functions. What we have is uncertainty given the current value function of the parameters, or given the current policy over the parameters. And we have this term, right, when we say we're going to minimize the divergence between our variational parameters and the true posterior, we wind up with this objective which basically says we should make our variational close to the prior and we should maximize the likelihood of the data. And this term over the right is going to come to dominate the objective as we see more and more and more data. But it's not really clear here what is the right notion of it's not like you just have a supervised learning problem, you've seen more data, you become more confident. As you go on and you're updating now, you have stale data, which is not from the distribution of states seen by the current policy. Precisely to what extent should this term on the right come to dominate? You could have a sort of arbitrary decision which just says it should be basically, its weight grows with the size of the replay buffer, but that's sort of an arbitrary decision. So in our case, this becomes something of a hyperparameter. It's worth being a bit sober about that, right? We have this tendency in a lot of reinforcement learning stuff to really hit the simulator many, many, many times to set a hyperparameter, and then ultimately to produce one final great plot where it seems like the model's learning really quickly, and we don't necessarily count all of the investigations we did in the first place to find out, okay, I can explore really efficiently if I had a well-tuned uncertainty predictor, but I can only get the well-tuned uncertainty predictor if I explored really inefficiently in the past. And that's sort of a critical point I would raise about my own work, and I think one that probably applies a bit more broadly. So what we find is that what ends up happening is it actually, in this case, I should actually start with a later plot. To start with, what we find is the task basically is hard enough. You don't find any reward signal besides just getting the guy off the phone as fast as you can. If you don't start off with some knowledge that the reward exists. So what ends up happening, right, is you never get a reward besides the one that tells you to end the dialogue quicker, because actually having a successful dialogue is difficult. So you basically wind up with a dialogue system that says goodbye. And the person's like, I would like to see a movie, like, goodbye. And then eventually the simulator has somewhere, the user simulator also says goodbye. We ended up doing is saying, what if you just had a crappy rule-based simulator that actually is going to do considerably worse? In our case, we tried to make the rule-based simulator as strong as we could, but still, we're not guided by some great principle. We believe, we have no reason to believe it's optimal, but at least we're able to use it and conduct enough dialogues, and it occasionally is right. So for example, it'll be kind of brute forcey, like it'll ask just like in sequence, like the 9 questions in a row, like what city are you in? What movie do you what genre do you like? What actor do you like? What time do you want to see the movie? Whatever. And assuming the user doesn't get fed up and get off the phone, then at least sometimes it gets the right answer. So we use the rule-based simulator to collect some number of successful dialogues, and we just start off the replay buffer containing those successive dialogues. So at least we have some signal that there is a reward besides just getting the person off the phone quickly. And that seems to be enough to get us out of that kind of failure mode. But it's still worth thinking about the fact that there's something a little bit crazy and unprincipled about what we're doing. Then we have two kind of settings that we evaluate in. One on the left is basically just we have the full statement of the problem. The one on the right, we actually have a whole bunch of additional. We start off with a subset of the problem where there's only certain attributes of the film available, either to the user or to the conversation agent, and the problem is changing over time. So like every 40 rounds, suddenly a new, in the beginning you only know names of movies, the time, the city, and then over time someone can request a specific theater, over time someone can ask questions about the actor or the genre or whatever. So it actually becomes a slightly harder problem with a slightly enlarged state space with some new inputs, both for the user simulator and for our system. And we find there's a few interesting things that are going on here. One is that it seems like all the sort of regular DQN things are sort of regular sort of alternative to epsilon greedy, like Boltzmann exploration or DQN bootstrap. They tend to quickly get to some slightly better than just get the guy off the phone level of reward, and then improve only very, very, very slowly. And in contrast, we improve, so it's like 50 dialogues per round. So we're talking about on the order of tens of thousands of dialogues, we're able to get to a pretty good policy. Like the best you could possibly do would be, maybe 17, 18 or something like this, or I don't know exactly, maybe it would be 20. Yeah, so our policies do end up exploring a lot faster. We also investigated some ways of combining our exploration strategy with also some intrinsic motivation. On the right side, our policies seem to be better at adapting to the changing environment than the kind of standard exploration strategies. So, some sobriety and limitations that, we're looking at the uncertainty over the parameters, but that's not necessarily, we actually want to have some uncertainty over the environment's dynamics. The heuristic seems to work well once we kind of get to an okay policy at improving it rapidly, but it depends crucially on one hyperparameter. It can converge to a bad trivial solution if we don't do the warm starting trick, and right, especially this case where it could assume the reward doesn't exist when the reward is sparse. That's the trivial way to show what kind of can go wrong. Yeah. So. Yeah. So that's done. What time are we? How are we doing on time?
6 minutes.
6 minutes. Okay. So just another thing that I was looking at is I just kind of this is early. This idea came kind of early in me starting to explore deep reinforcement learning. So I was the first time I was playing with some of these simulators, I set things up and I train and I get to see can I get it to do a good job on card pull? And card pull is a problem that's solvable. You should have a perpetually upright system that just holds the pull up. There's even an analytic solution to the problem, I believe. And what ends up happening is what happens if you just have an agent that's a continuously exploring agent that is just trying to learn card pull and you just continue to run things? What ends up happening is this is this chart over here in the bottom next to card pull is showing the number of time steps that it held the pull up, over time as it's learning. So you see it drops it a bunch of times, drops it a bunch of times, whatever, and then eventually it hits this point, those really high points mean that it's just surviving for thousands and thousands and thousands of steps, right? And it's not dropping the pull. And it turns out that what happens is we have this dynamic where we're updating our model based on recent trajectories. So we encounter something you don't want to happen, which is you drop the pull. The optimal policy we know should never drop the pull. So we encounter it a bunch of times, and we have experiences in our replay buffer that correspond to the pull being dropped. And then we update our policy, and eventually we arrive at a policy that doesn't drop the pull. Right? And now we have this policy that doesn't drop the pull, so it doesn't know that dropping the pull is a thing that could happen. And eventually, if you keep updating your policy, it might drift back towards one that's going to drop the pull again. And there's nothing to stop it from doing that, unless the rewards actually happen to be naturally shaped away such that, like, it enters some kind of regime of policy space where the reward shaping, even if you never see the poll being dropped, tells you shouldn't drop the poll. In the case of card pool, right, there's nothing to tell you that, like, certain kinds of behaviors are, like, more dangerous, right? Like, you could tell if someone's a bit, like, loose on the poll, like, it looks a bit reckless, like, it looks like it's gonna drop, like, it looks like it's in a dangerous situation. But that doesn't exist actually in the reward signal. The reward signal doesn't tell you you're being a little bit reckless with a poll, like, chill out. It just says, like, you get a point, get a point, get a point, get a point until you die, in which case you get this huge shock of, like, you're no longer getting the kind of reward that you're used to. So, right, you encounter a bad state, it enters a replay buffer, you learn to avoid it, then you forget that you learned to avoid it, and eventually you re-experience it again. And you could say, what if I just keep all the experiences that I had in the buffer and I never forget about anything? So on one hand, that could be a bit infeasible depending on the storage limits. Like, you could wind up to, depending on the system and how fast it's updated and how many experiences it has, this might be millions or billions of time steps that we're collecting. And even if we do that, basically we're just going to, as we're, like, randomly grabbing batches from the replay buffer, as they recede further and further back into the memory, they're going to be updated more and more infrequently. So, as long as you have a policy that's continuing to explore, you want to continue to explore your environment, but you never want to experience certain states. So the question here, and that we start off with this idea that, we're actually adding some kind of structure to the problem that isn't just in a generic reinforcement learning problem, right? Like, we don't start off with, like, in the most generic statement of RL, that there exists some kind of states that you never want to experience, right? It's possible that actually you're supposed to go through those states to discover the optimal reward. So what we're basically saying is that there exist states that the optimal policy should never experience, and in fact, it should never be even reachable within a couple steps from, right? So being, like, with a pole tilted heading at full velocity towards the, like, side of the wall is a state that you never want to enter, right? Because it's a state from which dying is reachable. Right, so we know that it's possible that there's some buffer zone as measured in, like, trajectory space. So our goal is to say, can we come up with a way that, given that the agent is at least able to recognize post hoc that it has entered, like, it has collected experiences from a catastrophic state, can it have something like the avoidance behavior? Like, it can, at least in the future, get a reward signal where it's not coming from having to make the mistake again, but coming from getting close to it. So our algorithm is basically to say, let's have two models, right? One model is going to collect just a short snippet of trajectories leading up to something bad happening. So you could think of this as, like, some, you want to be really speculative and intuitive. I have to be very careful now because I've been very critical of conflating explanation for speculation. But you could think of something like a traumatic experience, like, you get, like, you almost have an accident, and that's enough to, like, cause you to fix your behavior. You don't have to actually kill someone to be scared straight. We'd like to do something similar for the model. We'd like to send a negative reward when you enter something that looks like a state from which, the catastrophe was proximal. So what we're going to do is we're going to set some kind of radius. So, like, the case steps leading up to the catastrophic event are going to be added as positive examples of being near a catastrophe. We're also going to take random samplings of non-catastrophic states, and we're going to train a classifier that tries to recognize catastrophic, like, are you in a danger state or not in a danger state? And this is going to, now our danger model is going to provide a sort of auxiliary reward that is going to try to guide our, like, continually exploring policy from ever getting too close to a catastrophic state. This is the algorithm formally. It's, in the paper, so it's not so important to stress the details. And basically, you could find that we wind up in a situation where, we could dial up how big is that radius and how big is the penalty, and we can get an agent that'll adopt some extremely cautious behaviors, like, it doesn't get so much reward, but it tries never to die. But we actually find that it provides a good sort of inductive bias. So for a lot of these games, it's actually, like, a true thing that you want to avoid dying. And, like, a really good policy should not be near dying. So if we make, in the Atari game, dying the bad state, we actually find that sometimes we actually get more reward by adding, by sort of dirtying our reward signal. And, the sort of intuition might be that actually the optimal policy has this, still gets the same reward because it never, gets into danger. So we both sort of explore faster, and we also encounter many fewer of these catastrophes compared to the green line, which is your sort of baseline policy. So anyway, I do not need to fall back upon my active learning slides, so that's cool. It's been nice chatting with you. I guess that's all I have.